imagine you are an enterprise executive, right?
Yeah.
And you are overseeing this massive global infrastructure expansion.
Oh, the classic high-stakes scenario.
Exactly. You've got the server farms procured, you've hired the absolute brightest engineering talent, and you've leased premium real estate across 3 continents.
So millions of dollars already committed.
Oh, absolutely. The hardware is racked, the power is on, and you're literally just ready to flip the switch. You're about to bring thousands of remote workers and all these IoT devices online.
Right.
But then your lead network architect walks into your office and they point out a fatal flaw in the blueprint. And it's that the digital world has completely run out of real estate.
Just entirely out of space.
Literally, no new address is available. I mean, you can't connect a single new server. You can't onboard a single new employee laptop.
It sounds like a dystopian sci-fi scenario, right?
Yeah.
Designed to just give CIOs night terrors.
It really does. But the crazy part is, this isn't fiction. The world actually exhausted the supply of standard IP addresses way back in 2011.
Yeah, over a decade ago.
Right. And yet, the hyper-connected global marketplace hasn't just, collapsed into digital anarchy. Your multi-million-dollar data streams are still flowing perfectly.
Which is pretty miraculous if you think about it.
So the question is how? What are the hidden mechanisms keeping your enterprise from just dropping into the void? Today, we are going to uncover the architectural magic tricks that keep modern businesses alive.
And it's some pretty brilliant engineering.
It really is. And if you are an IT leader who wants to ensure your infrastructure never hits a wall, so you always maintain a competitive edge in this, hyper-connected marketplace, make sure to like, subscribe, and share this deep dive.
Absolutely.
And definitely check the description below for access to additional corporate resources, diagrams, and some advanced technical reading tailored specifically for executives.
Because honestly, the digital highway essentially ran out of pavement 15 years ago. So network engineers decided to just fundamentally alter the nature of space and routing.
They literally bent the rules of digital physics.
Yeah, just to keep the traffic moving. And for anyone sitting in a leadership position, understanding how this traffic flows and, the limitations of the workarounds we've built, it's completely non-negotiable.
Right. Which brings us to today's topic. Welcome to Chapter 5. The network and transport layers, which serves as part 5 in our 15-part strategic arc.
Moving right along.
Yeah. To set the stage, let's look at where we left off. So in Chapter 4, the physical and data link layers, we explored the foundational hardware.
The literal nuts and bolts.
Exactly. We examined the physical fiber optic cables trenched under the oceans, the local switches in your telecom closet, and those MSC addresses burned right into your network interface cards.
Right. We established how Layer 2 networking manages local endpoint connectivity, within a single broadcast domain.
But Layer 2 is strictly about the immediate neighborhood, right?
Yeah, exactly. It dictates how a server talks to a printer in the exact same room, or how an employee's laptop communicates with the Wi-Fi access point right above them in the ceiling.
It's all physical hardware addresses.
Exactly. But modern enterprises, they're not confined to a single floor of a single building anymore.
No, not at all. You have a marketing team in New York that needs to pull real-time database analytics from a server rack that's, sitting in Frankfurt, Germany.
Right. Which perfectly frames our mission for today's deep dive.
Yes, it does. We are leaving the local area network behind and zooming out to the planetary scale. Our focus is Chapter 5. The network and transport layers.
Big picture stuff today.
The biggest. Yeah. We are going to dissect the exact journey data takes as it navigates the global maze, jumping across completely disparate networks, crossing oceans, and arriving at its exact destination without corruption.
So we are basically bridging the gap between local physical reality and global digital strategy.
Exactly.
And to do that effectively, we really need to introduce the architectural blueprints that define global communications, mainly the OSI reference model and the TCP/IP reference model.
Okay, let's ground these abstract models in something tangible, because otherwise it just gets too theoretical.
Good idea.
I like to look at network layers, like a highly optimized corporate logistics and shipping department.
Okay, I like where this is going.
So the lower layers, the physical and data link layers from our last chapter, they are your local warehouse workers.
Right, the boots on the ground.
Exactly. They are the ones physically driving the forklifts, loading the pallets onto the trucks, and dealing with the immediate, tangible transfer of goods right off the loading dock.
But those warehouse workers, they have absolutely no idea how a shipping container is supposed to navigate from, say, a factory in Shenzhen all the way to a retail distribution center in Chicago.
No, of course not. They just know how to put the box on the first truck.
Right, and figuring out the rest of the journey requires a completely different division of the company. Which brings us to OSI Layer 3, the network layer.
So in our logistics analogy, what is Layer 3?
Layer 3 is the strategic routing division at corporate headquarters.
Ah, okay. The planners.
Exactly. The personnel in this division never touch a physical box. Instead, they just look at global maps. They evaluate the interstate highway systems, the transoceanic shipping lanes, the rail networks.
They're doing the heavy logistical math.
Right. They calculate the optimal path for the cargo based on, current traffic conditions, border customs, and overall route efficiency.
Okay, that makes perfect sense. And sitting in the office right next to them is OSI Layer 4, the transport layer.
Yes.
I see Layer 4 as the meticulous quality assurance manager.
The QA department.
Right, because the routing division might figure out the path, but the QA manager guarantees the shipment actually survives the journey.
They're enforcing the standards.
Exactly. They dictate how the cargo is packed, they pace the shipments so the receiving dock in Chicago doesn't get, completely overwhelmed and start dropping boxes, and they demand a signed receipt of delivery.
And if a box goes missing in transit?
The QA manager is the one who notices and immediately ships a replacement.
I really like that analogy. The beauty of it is how neatly it maps to the actual technical frameworks we rely on.
It translates pretty cleanly, right?
It does. In the theoretical 7-layer OSI model, you have Layer 3 as the network layer and Layer 4 as the transport layer.
Right.
But when we shift over to the practical TCP/IP model, which is the actual suite of protocols running the modern internet, those functions map directly to the internet layer and the transport layer.
So the OSI model gives us the deep theoretical design, while the TCP/IP model provides the actionable software that's actually running on your enterprise servers right now.
Exactly. It's theory versus application.
Okay, let's isolate the strategic routing division first. OSI Layer 3.
Okay, let's dive in.
What are the specific technical responsibilities of this layer when a piece of data leaves a corporate laptop?
Well, primarily, Layer 3 provides logical network addressing, and it supports the massive routing technologies that direct packets across completely different networks.
So when a packet of data leaves your local warehouse, Layer 3 is what allows it to transcend the local hardware.
Exactly. It stops relying on the physical MSE addresses of local machines, those burned-in addresses we talked about last time.
Right.
Instead, it starts using logical IP addresses to navigate the global internet.
Which is the domain of the Internet Protocol, or IP. But IP isn't acting alone in this layer, is it?
No, not at all. Our sources highlight several critical protocols operating here. For instance, there's the Internet Control Message Protocol, or ICMP.
What is the business value of ICMP for an IT manager? Like, why should they care?
Think of ICMP as your primary diagnostic radar. It queries device status and network availability.
Okay, so it's checking if things are alive.
Exactly. When an IT administrator opens a terminal and types the ping command to see if a remote branch office server is online, they are utilizing ICMP.
Oh, so that's what ping is actually doing under the hood.
Yeah. It sends a small echo request, and if the remote server is alive and reachable, it sends an echo reply.
And what if it's not reachable?
Well, if a router drops a packet because a network is unreachable, it uses ICMP to send an error message back to the source.
So without ICMP, your network administrators would be flying completely blind when troubleshooting global outages.
Completely blind. It's essential. Then we also have Internet Protocol Security, or IPSec, sitting at this layer, which feels particularly relevant given the state of modern cyber warfare.
Oh, absolutely. Cybersecurity is top of mind for everyone right now.
Right, and IPSec is foundational to enterprise security. It operates directly at Layer 3 to authenticate and encrypt IP packets.
So this is how we build secure tunnels.
Exactly. This is the underlying technology that allows an organization to build secure, virtual private networks, or VPNs.
So if you have an executive sitting in a coffee shop connecting to the corporate intranet,
IPSec can wrap their data in an encrypted tunnel right there at the network layer.
and even if a bad actor intercepts the packets on the public Wi-Fi, they only see scrambled ciphertext.
Exactly. It's totally illegible to them.
Now, the sources also mention legacy protocols at Layer 3, like AppleTalk, though I assume IP has effectively monopolized this space in the modern era.
Oh, yeah. IP is the undisputed sovereign of Layer 3 today. AppleTalk is basically a museum piece at this point.
Right.
However, understanding the layer's capability goes beyond just knowing the dominant protocol. For leaders, Layer 3 is vital because it dictates global topology.
How so?
Well, this is where virtual circuits can be established. A virtual circuit is a predefined logical path between two nodes across a complex network.
Oh.
By manipulating Layer 3 routing, managers can ensure reliable, prioritized paths for critical enterprise applications. It directly impacts how efficiently your global branches communicate with each other.
So Layer 3 successfully navigates the global maze.
Yeah.
It gets the data from New York to London.
Yes.
Now we elevate to Layer 4, the transport layer, the quality assurance manager in our analogy.
All right, so Layer 4 accepts the raw data from the upper application layers, the email clients, the web browsers, the database software.
The stuff the user actually sees.
Exactly. And it is tasked with providing transparent, reliable data transfer to the destination. It basically bridges the gap between the application's intent and the network's reality.
Okay, let's dissect the specific services Layer 4 provides, because this is where the engineering gets really fascinating to me.
It is pretty cool.
The first major service is flow control. What exactly does that mean in practice?
Well, flow control is essential for preventing digital avalanches.
Digital avalanches?
Yeah, imagine you have a massive state-of-the-art enterprise server in a data center, and it's trying to send a large video file to an employee's, say, 5-year-old smartphone that's connected to a weak cellular signal.
Okay, a huge mismatch in power.
Exactly. If the server transmits data at its maximum capacity, it will completely overwhelm the smartphone's processing buffer.
Because the phone just can't catch the data fast enough.
Right. The phone will start dropping packets, leading to massive data loss. So Layer 4 flow control utilizes a sliding window mechanism to pace the transmission.
How does the sliding window work?
It essentially allows the receiving device to say, hey, I can only handle 50 kilobytes at a time right now.
Oh, so it pushes back.
Exactly. The sender adapts its speed dynamically, ensuring smooth data transfer without overwhelming the receiver.
That makes perfect sense. The next service is fragmentation and reassembly.
Right.
I imagine this is like trying to ship an entire fully assembled car through the postal service. You just can't do it.
No, the mail truck is too small.
Right. You have to take the car apart, put the parts into smaller boxes that actually fit in mail trucks, and then the recipient has to rebuild the car in their driveway based on an instruction manual.
That is a highly accurate comparison, actually. Networks have a maximum transmission unit, or MTU.
MTU.
It is the strict size limit for a single packet of data on that network. So if an application tries to send a 10 megabyte PDF document, Layer 4 chops that document up into thousands of smaller network digestible segments.
And how does it know how to put it back together?
It slaps a sequence number on each segment.
Ah, the instruction manual.
Exactly. When those thousands of individual packets arrive in London, the receiving Layer 4 looks at the sequence numbers and pieces the PDF back together perfectly before handing it up to the user's screen.
That's brilliant. And tied directly into that reassembly process is error control and acknowledgement of delivery, right?
Right. This is the signature on the delivery receipt we talked about. Layer 4 keeps track of every single segment it sends.
It's watching everything.
It is. If it sends segment number 45, it starts a timer.
A literal countdown.
Yep. If it doesn't receive an explicit acknowledgement from the destination device before that timer expires, it assumes segment 45 was lost somewhere over the Atlantic Ocean.
And what does it do?
It just automatically transmits a duplicate. It doesn't even bother the user. It just fixes the problem.
Okay, but setting up a timeline here. This implies a profound difference in philosophy between the routing division and the QA manager.
How so?
Well, if Layer 3 already routed the packet successfully across the globe using IP, why is Layer 4 doing all this aggressive checking and retransmitting? Isn't the routing protocol sufficient?
That's a great question. The fundamental reality of the internet is that Layer 3 routing is strictly best effort.
Best effort. That doesn't sound very reliable.
It isn't. The internet protocol simply looks at the destination address, decides which cable to push the packet down next, and immediately forgets about it.
It just fires and forgets.
Exactly. It does not care if the packet arrives. It does not check if the packet was corrupted by a solar flare or a faulty switch. IP just routes and moves on to the next packet.
It's the equivalent of a paperboy who throws the newspaper aggressively in the general direction of your house while riding his bike and never looks back to see if it landed safely on the porch or if it shattered your front window.
That is the perfect visualization of best effort delivery.
It's just chaos.
It is, and that is exactly why the transport layer offers different protocols depending on the application's tolerance for risk. The most prominent one is the Transmission Control Protocol, or TCP.
Okay, TCP. We hear that acronym all the time.
Right. TCP is what provides that reliable end-to-end communication channel. It wraps the data in a TCP envelope, it manages the sequence numbers, executes the error control, and demands those delivery acknowledgments.
So it's the strict QA manager.
Yes. TCP provides an absolute guarantee that the data will arrive intact and in the correct order.
But the sources also highlight UDP, the User Datagram Protocol. Does UDP offer those same ironclad guarantees?
Not at all. UDP offers zero guarantees.
Wait, really? None.
None. It provides best effort delivery, mimicking the underlying nature of IP itself. There is no flow control, no sequence numbering, and absolutely no error recovery.
So if a packet gets dropped,
UDP doesn't even notice, let alone try to resend it.
from a corporate strategy perspective, why would a CIO ever authorize the use of a protocol that actively allows data to just vanish? I mean, if I'm running an enterprise, I want every single piece of data guaranteed.
It comes down to a ruthless calculation regarding the trade-off between absolute reliability and real-time speed.
Okay, walk me through that.
Well, TCP's ironclad guarantees require a massive amount of overhead. Establishing the connection takes time. Constantly acknowledging packets takes time. Retransmitting lost data introduces significant latency.
Which is fine if I'm sending a quarterly financial ledger or a legal contract.
Exactly. For a financial ledger, TCP is mandatory. If you lose a single packet containing a critical zero, the entire ledger is mathematically corrupt.
Yeah, that would be a disaster.
Right. So you gladly accept a slight delay in transmission to ensure the file is pristine. But consider a global all-hands video conference with your CEO.
The dynamic changes completely.
Radically, if you are using TCP for a live video feed and a single packet representing one frame of video is lost somewhere in a router in Paris,
What happens?
TCP will halt the entire process. It will refuse to show the next frames, send a request back to the source to retransmit the missing frame, wait for it to arrive, and then insert it.
Oh, so your video feed would just constantly freeze, stutter, and buffer into unwatchable chaos.
Exactly. Everyone hates buffering.
Whereas with UDP, if a frame drops,
The protocol just ignores it and pushes the next available frame to the screen.
you might get a little glitch.
Right. The human eye might perceive a microscopic flicker or a slight pixelation artifact, but the live stream continues uninterrupted in real time. Speed and momentum are far more valuable for voice and video than perfect data integrity.
That makes total sense. Therefore, network architects deploy TCP when integrity is paramount and UDP when velocity is the priority.
Spot on.
Let's transition our focus back down to the workhorse underneath it all. OSI Layer 3 and the Internet Protocol.
The decentralized engine.
Right. This is the decentralized engine of the digital age. A critical characteristic highlighted in the architecture is that IP treats every single packet, often referred to as a datagram, completely independently.
It does.
It does not group packets belonging to the same file together at all.
And the architectural philosophy behind that design is one of extreme resilience.
Yeah, resilience to what?
Well, IP networks were originally conceptualized during the Cold War with the ability to survive catastrophic physical damage to the infrastructure.
Like a nuclear strike.
Basically, yeah.
Yeah.
Therefore, there is absolutely no central management authority. There is no master control node dictating how traffic flows across the global grid.
To an outsider, stripping away central management sounds like a recipe for total chaos.
Yeah.
I mean, how does a massive corporate data center rely on a system with no master plan?
The system functions precisely because it replaces a brittle master plan with dynamic autonomy.
Give me an example.
Okay, imagine you have a primary fiber optic backbone connecting your New York headquarters to a data center in Chicago. Suddenly, a construction crew in Pennsylvania accidentally severs that fiber cable with an excavator.
Which actually happens all the time.
It really does. If IP networks were centrally managed with rigid, pre-planned paths, every piece of data destined for Chicago would hit that severed cable and die.
The network would face a catastrophic outage until human engineers intervene to update the master plan.
Exactly. But because IP is decentralized, the system reacts organically.
How fast?
Instantaneously. The routers in New York detect that the path through Pennsylvania has gone dark. They immediately consult their dynamic routing tables, communicate with neighboring routers, and autonomously calculate a new path.
Just on the fly.
Yep, perhaps routing the traffic south through Washington, D.C., across to Dallas, and then up to Chicago. The traffic flows around the physical damage like water flowing around a newly dropped boulder in a stream.
That level of self-healing is incredible. However, Treating every packet as an independent entity navigating a dynamic web introduces a significant logistical hurdle.
It does.
If I'm sending that 1,000-page M&A contract, packet number 1 might take the northern route through Canada, while packet number 2 might take the southern route through Texas.
And because the routing conditions change by the millisecond, packet number 2 might arrive in Chicago long before packet number 1.
The data arrives entirely out of sequence.
Entirely out of sequence.
Okay.
Furthermore, during times of extreme congestion, a router might just become overwhelmed and drop a packet entirely.
Which brings us full circle back to why we need TCP at layer 4 sitting at the destination, right? Waiting patiently to organize the chaos, resequence the out-of-order packets, and request redelivery for anything that the network dropped.
Exactly. They are a symbiotic pair. IP provides the rugged, unkillable delivery network, and TCP provides the civilized order required for actual business applications.
Okay, let's put a magnifying glass on the actual package being transported, the anatomy of an IPv4 packet header.
The shipping label.
Right. When the network layer receives a segmented piece of data from the transport layer, it encapsulates it. It slaps a digital shipping label onto the front of the data before pushing it down to the physical cables. What crucial metadata is inscribed on this IP header?
The header contains roughly a dozen different fields, but a few dictate the core functionality of the internet. First and foremost, you have the source IP address identifying the exact machine that generated the packet, and the destination IP address identifying the target machine.
Right, because without those, routing is impossible.
Exactly. But beyond the addresses, there are ingenious mechanical features built into the header. Let's look at the time to live, or TTL field.
Time to live. What is the engineering logic behind a time to live mechanism?
The PTL is essentially a digital hot potato mechanism.
Hot potato.
Yeah, it is a specific field in the header that contains an 8-bit numeric value, typically starting at 64 or 128, depending on the operating system.
Yeah.
Every single time this packet passes through a router on its global journey, that specific router is mathematically required to decrease the TTL value by 1 before sending it on to the next hop.
Oh, wow. So it is a literal countdown timer attached to the data.
Yes. And when that countdown timer hits 0, the router holding the packet does not forward it.
What does it do?
It simply deletes the packet from memory and sends an ICMP error message back to the source saying, time exceeded.
On the surface, programming network infrastructure to actively assassinate corporate data seems counterintuitive. I mean, why do we want our packets to have a finite lifespan?
We implement it to prevent the network from choking to death on its own confusion.
How so?
Remember that decentralized dynamic routing we just praised?
Yeah, the water flowing around the boulder.
Right. Well, it isn't flawless. Sometimes routing tables become misconfigured or get out of sync. You might have a packet trying to reach a server in Tokyo.
Okay.
A router in Los Angeles looks at its table and says, the best path to Tokyo is through Seattle. So it sends the packet to Seattle.
Makes sense.
But Seattle's routing table has a glitch, and it thinks the best path to Tokyo is back through Los Angeles.
Oh, no. So the packet gets trapped in a digital ping pong match.
It becomes an infinite routing loop. LA sends it to Seattle, Seattle sends it back to LA endlessly at the literal speed of light.
That's terrifying.
Now imagine a broken application generating thousands of these lost packets per second. Without a TTL mechanism, those packets would circulate the global internet forever.
Just building up and building up.
Exactly. Over a matter of hours, these immortal looping packets would consume all available bandwidth on the global fiber lines, causing a catastrophic denial of service condition that would take down the entire internet.
Wow. So the TTL ensures that lost packets gracefully age out and die before they can cause structural damage.
Exactly. It's self-cleaning.
That is elegant engineering. Another vital component our sources detail is the IPv4 header checksum.
Right. The checksum is an integrity mechanism. Before a router transmits an IPv4 packet, it runs a specific mathematical algorithm against all the bits contained in the header to generate a numeric value, the checksum.
And it writes this value into the header.
Yes. When the packet arrives at the next router, that receiving router performs the exact same mathematical calculation on the header it just received.
And if the resulting number matches the checksum written in the header, the writer knows the metadata is pristine.
Correct. But if the packet passed through a section of copper cable that experienced heavy electromagnetic interference, or if a failing switch flipped a 1 to a 0 in the destination address, the math won't add up.
The calculated checksum will differ from the embedded checksum.
Exactly. And the router immediately identifies that the header is corrupted and drops the packet. It refuses to route based on compromised data.
This deep dive into the IPv4 structure brings us directly back to the existential crisis we highlighted in our opening hook, the IPv4 exhaustion crisis.
Right, running out of real estate.
To understand the panic, we need to do the math on the protocol itself.
It boils down to a rigid mathematical constraint established in the 1970s.
Right. An IPv4 address is fundamentally a 32-bit binary number. But for human readability, we don't write out 32 ones and zeros.
That would be a nightmare.
It really would. We use what is called dotted decimal notation. We break the 32 bits into 4 separate 8-bit chunks, known as octets, and separate them with periods.
Right.
Because an octet is 8 bits, its decimal value can only range from 0 to 255. So a classic IPv4 address looks something like 192.168.1.50.
The architecture is elegant, but that 32-bit limit dictates the absolute ceiling of the system. 2 to the power of 32 yields approximately 4.29 billion possible unique IP addresses.
Now, if you are a DARPA researcher in 1978, connecting a dozen university mainframes together, 4.29 billion addresses sounds like infinity.
Oh, it was an astronomically large number for the era. They simply could not conceive of a future where billions of individual humans would carry supercomputers in their pockets.
Or where internet-connected sensors would be embedded in manufacturing lines, refrigerators, and automobiles.
Exactly. The IoT explosion wasn't even a concept.
But the exhaustion wasn't solely driven by the explosion of devices, was it? It was heavily accelerated by how aggressively wasteful the original allocation system was.
Oh, incredibly wasteful.
Let's examine the original Classful network architecture because it serves as a masterclass in poor resource management.
In the early internet, authorities organized IP addresses into strict, inflexible categories based on the size of the requesting organization. They partitioned the 4.29 billion address pool into 5 classes, A, B, C, D, and E.
But for corporate networks, only A, B, and C matter, right?
Right.
So how are those classes structured?
It was based on prefix lengths. Class A networks were reserved for massive governmental or corporate entities. A Class A address always started with a binary 0. It used only the first 8 bits for the network identity, leaving a massive 24 bits for host addresses.
And what does that translate to in actual numbers?
It meant a single Class A network contained over 16.7 million usable IP addresses.
Wait, 16 million addresses handed to a single entity?
Yes, literally 16 million.
That is absurd.
It gets worse. Class B was intended for medium to large organizations. It used a 16-bit network prefix, leaving 16 bits for hosts. If you were assigned a Class B block, you were given exactly 65,536 IP addresses.
Okay, and Class C was the smallest tier.
Yes. Class C utilized a 24-bit network prefix, leaving only 8 bits for host devices. A Class C block provided exactly 256 addresses.
Looking at this through a modern business lens, the flaw is glaringly obvious. Imagine you are the CIO of a growing logistics firm in, say, 1994.
Yeah.
You have 1,500 employees and you want to network their workstations. You go to the internet authorities to request an IP allocation. A Class C network only gives you 256 addresses, which is entirely inadequate. So you request a Class B block.
And because you legitimately needed more than 256 addresses, the authorities would approve that Class B request.
So they hand you a Class B block containing 65,536 public IP addresses. Your IT team assigned 1,500 of them to your employees. What happens to the remaining 64,000 addresses?
They sit completely dormant.
Just unused.
Completely unused. They are legally and technically bound to your organization's routing prefix. No other company, university, or ISP anywhere in the world can use them.
So you have effectively locked away 64,000 pieces of vital digital real estate that you will never use.
Exactly. Multiplying that scenario across thousands of growing companies in the 90s, you can see how we burned through 4.29 billion addresses at breakneck speed.
It was a digital land grab.
It was. The engineering community saw the cliff approaching, and they realized the rigid Class A, B, and C system was a disaster. To delay the inevitable, they introduced a much more granular system, CIDR.
CIDR. What does that stand for?
Classless interdomain routing. It was an emergency architectural pivot. It completely abolished the rigid boundaries of Class A, B, and C networks. It empowered the Internet Assigned Numbers Authority, the governing body for IPs, to slice up the address space with surgical precision.
We don't want to get bogged down in reciting binary code, but as a manager, I need to understand the mechanism. How does CIDR actually allow for this surgical slicing?
It operates by utilizing a subnet mask. Think of a subnet mask as a sliding fence on wheels.
A sliding fence.
Yeah. In the old Classful system, the fences were nailed to the ground. You either got a tiny yard, a medium yard, or an impossibly massive estate. There was no in between.
Right.
CIDR unbolted the fence. A subnet mask is a contiguous string of binary ones that visually overlays the IP address. Wherever there is a 1 in the mask, that portion of the IP address represents the overarching network. Wherever there is a 0, that portion represents the specific host device.
So by sliding that fence left to right, by changing the number of ones in the subnet mask network, engineers could carve out custom-sized network.
Exactly. If a company came to the authorities needing exactly 1,000 addresses, the engineers didn't have to hand them a block of 65,000. They could calculate a specific subnet mask, say a 22, which uses 22 bits for the network, and hand the company a block of 1,024 addresses. The remaining 64,000 addresses were saved for other organizations.
That is so much more efficient. And beyond conservation, subnetting offers a massive strategic advantage for internal corporate security and performance. A manager can take their allotted IP block and use subnetting to carve their own internal network into isolated segments.
That is a critical operational application. You can create one subnet for the human resources department and a completely different subnet for the engineering floor.
Why does that matter?
By placing frequently communicating nodes like engineers and their code repositories on the same specific subnetwork, you confine their heavy data traffic to local switches.
Oh, so it doesn't clog up the whole network.
Right. It prevents their massive file transfers from congesting the primary corporate routers. Furthermore, you can apply strict firewall rules between the subnets.
Ensuring an infected laptop in marketing cannot spread malware laterally into the secure HR databases.
Exactly. It's containment.
But CIDR, brilliant as it was just a tourniquet on an arterial bleed, right? The fundamental mathematical reality of 4.29 billion total addresses remain unchanged.
Sadly, yes.
The pool officially ran dry. So the ultimate question for any enterprise architect building a network today is this. If there are no public IPv4 addresses left to buy, how do I connect 10,000 new corporate devices to the internet tomorrow morning?
You utilize a masterful combination of private IP architecture and network address translation, or NAT. This combination is literally the duct tape holding the modern internet together.
Let's unpack the private architecture first. What makes an IP address private?
Decades ago, anticipating the exhaustion crisis, network engineers drafted a document called RFC 1918. They took a step back and carved out 3 specific blocks of IPv4 addresses.
Which ones?
One from the Class A range, which is the 10.x.x.x network, one from Class B, and one from Class C, which is the ubiquitous 192.168.x.x network.
Right. Everyone has seen that one on their home router.
Exactly. They declared these specific blocks as private. The core internet backbone routers were explicitly programmed to recognize these addresses as non-routable.
Meaning, if I try to request a public website using a private IP address as my source, the internet's core routers will look at my packet, laugh, and drop it in the trash.
Precisely. They will not route private traffic over the public internet. The strategic genius of this is that because these addresses cannot reach the public web, they do not need to be globally unique.
Oh.
Yeah. A corporation in Tokyo can use the 10.0.0.0 network for its internal computers, and a competing corporation in London can use the exact same 10.0.0.0 network simultaneously.
You do not need permission from the internet authorities to use private IPs.
No permission needed. You can assign millions of them inside your own buildings.
Okay, that solves the internal routing problem beautifully. But it introduces a massive external problem. Those employees still need to access cloud software, read the news, and send external emails.
Right.
If their private IPs are non-routable, how do they talk to the outside world?
That is where the translation magic of NAT comes into play, specifically a variant called Port Address Translation, or PAT.
Where does PAT live?
PAT operates at the edge of your network, typically living inside your corporate firewall or edge router.
Let's trace a concrete business scenario to see exactly how PAT operates under the hood. Suppose we have a mid-sized architectural firm.
Okay, an architectural firm.
Inside their office, they have 200 high-end rendering workstations. For internal routing, the IT team has assigned them private IPs in the 192.168.1.0 subnet. So workstation 1 is 192.168.110, workstation 2 is 0.101, and so on.
But the firm was only able to lease a single solitary public IP address from their telecom provider. Let's say that public address is 172.124.0 or 0.0.
Okay. Now, workstation 192.168.1000 needs to download a massive CAD file from a public cloud server. It builds a packet. The source IP is its private address. The destination IP is the cloud server. It sends the packet to the corporate firewall. What's the firewall do?
The firewall intercepts the packet. It knows that if it forwards the packet as is, the internet will drop it because the source is private.
Right.
So the firewall engages port address translation. It forcefully strips the private internal IP, the 192.168.1.100, out of the packet header. It replaces it with the firm's one legally routable public IP. 172.124.0.0.0.
Now, the packet has a public return address. But here is the logistical nightmare. If all 200 workstations are browsing the web simultaneously, and the firewall is rewriting all their packets to look like they came from 172.124.0.10.
Yes.
When the cloud server sends the CAD file back to that public IP, how does the firewall know which of the 200 internal workstations actually requested it? I mean, they all look identical from the outside.
Because the firewall didn't just translate the IP address, it also translated the layer 4 port number.
Oh.
When the firewall rewrites the outbound packet, it appends a uniquely generated ephemeral port number to the public IP. For example, it might change the source to 172.124.0.0, port 50,001.
And it logs that specific transaction in its memory.
Crucially, it builds a NAT translation table. The table says, any incoming traffic from the internet destined for port 50,001 truly belongs to internal workstation 192.168.1.100.
Wow.
So when the cloud server replies, it addresses the packet to port 50,001. The firewall receives it, consults the translation table, strips off the public IP, restores the private IP, and hands the CAD file down to the exact workstation that requests it.
And it performs this sleight of hand thousands of times per second.
Millions, even. Unlocking the ability to multiplex thousands of internal devices behind a single public IP address.
That's incredible, but managing the assignment of these internal private addresses manually would be a nightmare. I assume corporate IT teams aren't walking around typing 192.168 addresses into every single employee laptop.
No, definitely not. They rely on DHCP, the Dynamic Host Configuration Protocol.
How does that work?
When an employee opens their laptop and connects to the corporate Wi-Fi, the laptop sends a DHCP Discover broadcast across the local network, essentially shouting, "Hey, I need an IP address." The DHCP server hears the broadcast, selects an available private IP from its configured pool, and sends a DHCP offer. The laptop requests the offered IP, and the server acknowledges it.
So it's an automated lease.
Exactly. Leasing the IP address to the laptop for a specific duration, along with vital configuration data like the subnet mask and the default gateway router.
If you are an IT leader, the strategic takeaway here is profound. Private IPs, NAT, PAT, and DHCP are the foundational pillars of modern corporate network design.
They absolutely are.
Not only do they circumvent the IPv4 exhaustion crisis, but they provide an inherent layer of cybersecurity.
That's a huge point.
Because your internal workstations use non-routable private IPs, they are effectively invisible from the public internet. A hacker cannot directly scan or target an employee's laptop from the outside because the laptop simply doesn't exist on the global routing table.
Right. It is safely hidden behind the firewall's NAT process.
It is a phenomenal workaround.
It is. But we must be honest, it is still just a workaround. We have stretched the 32-bit architecture to its absolute breaking point.
The duct tape is stretching.
Exactly. The global internet is groaning under the computational weight of maintaining these massive NAT translation tables. The complexity of routing through multiple layers of NAT, especially for real-time peer-to-peer applications, is just staggering. We required a permanent, structurally sound solution.
Which brings us to the future of the internet, which is slowly becoming the present. IPv6, the 340 Undecillion address network.
The primary engineering mandate for IPv6 was simple but monumental: solve the address space limitation permanently.
And how do they do it?
To achieve this, the architects abandoned the 32-bit structure of IPv4 and quadrupled the address length to a staggering 128 bits.
Let's try to comprehend that scale. 2 to the power of 128 yields over 340 Undecillion unique addresses.
It's a ridiculous number.
That's the number 340 followed by 36 zeros. Our earlier analogy about assigning an IP to every atom on Earth is mathematically sound, but it's hard to visualize.
It really is.
Try this. 340 Undecillion is so vast that you could assign a unique, publicly routable IP address to every single blade of grass on the surface of the Earth, and you would still have enough addresses left over to network the entire Milky Way galaxy.
The human brain just struggles to process numbers of that magnitude, but the business implication is clear. Under IPv6, the concept of address scarcity ceases to exist. We will never, ever run out.
But dealing with a 128-bit number presents a massive usability problem. We obviously can't use the simple four-number dotted decimal notation of IPv4. It would be way too long.
No, the numbers are way too large. IPv6 addresses are expressed using hexadecimal notation.
Hexadecimal.
Yeah. They are structured as 8 groups of 4 hexadecimal digits, with each group separated by a colon. Hexadecimal is a base 16 system, meaning it uses the numbers 0 through 9 and the letters A through F to represent values up to 15.
Okay, structurally, how are these massive addresses divided between the network identity and the host identity?
They adopted a highly standardized symmetrical split. The first 64 bits, the first 4 groups represent the network routing prefix. This identifies your ISP and your specific corporate network.
And the second half?
The latter 64 bits, the final 4 groups, represent the specific interface identifier, the host itself.
And there's a fascinating automation feature built into that host ID, isn't there?
Yes, there is. In many IPv6 configurations, a device can utilize a process called SLAC. That's Stateless Address Auto-Configuration.
How does SLA work?
The device takes its own physical 48-bit MP address, splits it in half, inserts a specific 16-bit hex value right in the middle, and flips a specific bit to dynamically generate its own globally unique 64-bit host ID.
Wow.
It completely eliminates the need for a DHCP server in many environments. The device practically configures itself the moment it connects to the network.
That is incredibly efficient.
Yeah.
But we have to address the elephant in the room: human administration.
Oh, yes.
The humans. An IT administrator typing out a full, uncompressed IPv6 address is staring down a nightmare of alphanumeric characters.
Typing out 8 groups of 4 hex digits guarantees human error. A single typo brings down a server. Recognizing this, the Internet Engineering Task Force established strict, logical rules for address compression to make these monsters manageable.
Yeah, looking at a standard IPv6 address, it's immediately obvious that many of these groups contain nothing but zeros. There has to be a mathematical shortcut to collapse that empty space.
There are 2 primary rules you must apply to compress an address. Rule 1 is simple. Within any of the 8 groups, you can drop the leading zeros.
Okay, give me an example.
So if a group is written as :0053:, you simply write :53:. If a group is :0db8:, it becomes :db8:.
That trims it down, but it doesn't solve the massive blocks of empty space. What is the second rule?
Rule 2 is the heavy lifter. You can replace a consecutive sequence of groups that contain only zeros with a double colon.
Just 2 colons next to each other.
Exactly.
But the sources are very specific about a limitation here. You can only use the double colon once in a single IPv6 address. Why can't I use them multiple times to compress different empty sections?
Because if you use the double colon twice, the computer's network stack wouldn't know how to reconstruct the full 128-bit address.
Why not?
An IPv6 address must always have exactly 8 groups. If an address has 2 empty groups, some data, and then 3 empty groups, and you compress both gaps with a double colon, the computer sees the compressed string but doesn't know how many zeros to unpack into the first gap versus the second gap.
Oh, I see. It loses the mathematical reference point.
Exactly. By strictly limiting the double colon to a single use per address, the computer simply counts the visible groups, subtracts that number from 8, and fills the single gap with the exact number of 0 groups required.
That makes perfect logical sense. But I foresee a practical issue for day-to-day business operations. Sometimes, as an executive or an admin, you have to type an IP address directly into a web browser, or script a file path to map a shared corporate drive. A URL inherently uses the colon character to specify port numbers like http://IP address :port 80. If an IPv6 address is literally constructed out of colons, won't the web browser completely misinterpret the syntax?
It absolutely would, which is why there are standardized workarounds for literal IPv6 addresses. If you are typing it into a web browser, the standard dictates that you enclose the IPv6 address in square brackets.
Square brackets.
Yeah. So the syntax becomes http:// open bracket, the IPv6 address, close bracket, :port 80. The brackets tell the browser, hey, everything inside here is the IP, the port number comes after.
What about Universal Naming Convention, or UNC paths, used for mapping network drives in Windows environments?
UNC paths do not support colons in the host name field at all. The solution there is to convert every colon in the IPv6 address to a dash and append the string.ipv6 literal.net to the end.
So it looks like a regular domain name.
Exactly. So a compressed address like 2001:DB8 :53 transforms into 2001-DB8-53.IPv6 literal.net. The operating system recognizes that specific domain suffix and translates it back into an IPv6 address internally.
Okay, let's confront a major strategic question derived from the underlying themes of our sources.
Hit me.
If IPv6 permanently solves the exhaustion crisis, eliminates the need for complex NAT translations, and includes built-in auto-configuration, why is the global transition moving so agonizingly slow?
It is remarkably slow.
We are a decade and a half past IPv4 exhaustion, yet IPv4 still dominates corporate enterprise environments. Who is to blame for dragging their feet?
It is a shared hesitation rooted in the fundamental laws of business risk and capital expenditure. Ripping out a functioning IPv4 infrastructure and replacing it with a fundamentally different, incompatible protocol is incredibly expensive.
And risky.
Highly risky. It carries a massive risk of catastrophic downtime. CIOs look at their networks running on IPv4 NAT and think, it's complicated, but it works. Why risk breaking the business to upgrade?
But the industry recognized this standoff, right? They didn't force a binary choice where a company had to switch off IPv4 on Friday night and boot up IPv6 on Saturday morning.
Exactly. The saving grace of this transition is the dual IP stack operating system. Modern networking hardware and operating systems are built with dual stack capabilities.
What does that mean?
This means they run the IPv4 protocol stack and the IPv6 protocol stack simultaneously, side by side, on the exact same network interface.
So what does that mean for an IT manager planning a migration?
It means you can deploy IPv6 incrementally. You can enable IPv6 on your core routers, and they will route IPv6 traffic for modern clients natively while continuing to route IPv4 traffic for legacy servers without any conflict whatsoever.
Oh, that's great. It removes the urgency of hard cutover and allows organizations to migrate at their own pace.
Precisely.
But as leaders, we want to push organizations toward pure IPv6 eventually, because it brings architectural efficiencies that IPv4 simply cannot match. Let's look at the header design. The IPv6 header was completely rebuilt from scratch.
It was streamlined for high-speed routing. One of the most significant changes was the complete removal of the header checksum.
Wait, we spent significant time earlier discussing how critical the IPv4 checksum was for detecting corrupted packets. Why would the architects of the new protocol strip out a vital security feature?
Because they realized they were forcing the network to double-check its math unnecessarily.
Unnecessarily?
Yeah. In modern network architecture, Layer 2 Ethernet frames have a cyclical redundancy check to ensure the physical transmission wasn't corrupted. Layer 4 TCP has a robust checksum to guarantee the payload is pristine.
Okay.
Making Layer 3 IP recalculate a checksum at every single router hop was like asking a redundant toll booth operator to audit the manifest of a shipping container when the warehouse already verified it and the recipient is going to verify it again.
Oh, so you fire the redundant toll booth auditor to speed up the highway.
Precisely. By eliminating the Layer 3 checksum, global routers no longer have to burn CPU cycles recalculating math for billions of packets per second. It massively reduces processing overhead and decreases routing latency across the entire internet.
Are there any brand new features added to the IPv6 header that executives should care about?
The most critical addition for enterprise applications is the flow label field.
Flow label.
This field allows a source device to mandate special priority handling by routers for specific streams of packets, bypassing default routing behaviors.
Give me a corporate use case for a flow label.
Consider a multinational healthcare conglomerate conducting remote robotic surgery over a network, or a financial institution executing high-frequency algorithmic trades.
Where milliseconds matter.
For those applications, latency is literally a matter of life and death, or millions of dollars. The flow label allows the application to tag its packets as VIP traffic.
So it jumps the line.
Yes. Every router that sees that flow label immediately prioritizes the packet, guaranteeing quality of service, or QoS, without having to deeply inspect the packet's contents. It bakes enterprise-grade prioritization directly into the core Internet protocol.
The strategic directive for our listeners is crystal clear. If you are a CIO, an IT director, or a network manager authorizing infrastructure upgrades, you must ensure that every single switch, router, and firewall you procure is natively dual-stack capable.
Absolutely essential.
Buying legacy IPv4-only hardware today is an act of accumulating massive technical debt You must future-proof your capital investments to ensure your enterprise can leverage the speed and QoS capabilities of native IPv6 when the final tipping point occurs.
The transition is accelerating. You want your infrastructure primed and ready, not acting as an anchor.
We've spent significant time analyzing how data crosses the global maze using logical IP addresses. But let's bring the focus back to the local reality, the concept of address resolution.
Right, coming back down to earth.
When our New York to London contract packet finally arrives at the destination corporate network in the UK, the global routing is finished. But the local switches on that floor do not understand IP addresses.
No, Layer 2 switches are ignorant of Layer 3 IP logic. They only understand physical MA addresses. The IP address successfully guided the packet to the correct neighborhood, but now the network stack has to find the specific front door of the CEO's laptop.
Right. It must translate the logical IP address into a physical hardware MAC address.
Exactly.
How does the network execute that translation locally?
In a traditional IPv4 environment, the network relies on ARP, the Address Resolution Protocol.
ARP.
Right. When the final router receives the packet destined for the CEO's IP address, it pauses. It broadcasts an ARP request across the entire local network segment. It essentially shouts to every device in the room, "Hey, who currently holds IP address 192.168.145? Please reply with your physical MAC address."
The CEO's laptop hears the shout, recognizes its own IP, and sends a targeted reply containing its MAC address.
Exactly. The router caches that MSC address in its ARP table, wraps the IP packet inside a Layer 2 Ethernet frame addressed to that specific MSC, and finally pushes the data across the physical cable to the laptop.
But what if our forward-thinking manager has fully upgraded the London office to an IPv6 network? Does ARP still work?
No, ARP is entirely obsolete in an IPv6 world. It relies on broadcast traffic, which IPv6 was explicitly designed to minimize for efficiency reasons.
So what replaces it?
IPv6 utilizes NDP, the Neighbor Discovery Protocol. NDP performs the exact same critical function, mapping logical IPs to physical MACs, but it does so using sophisticated multicast messaging built natively into the ICMP v6 framework.
Got it. Whether it's ARP or NDP, address resolution is the critical final millimeter of the marathon.
It really is.
Okay, that handles the machine-to-machine translation. But there is another layer of address resolution that is arguably the most important for daily business operations, translating human intent into machine logic. As an executive, I never open my web browser and type 172.21.201.176 when I need to order office supplies. I type Amazon.com.
You are interacting with DNS, the domain name system. Address resolution is not just about routing hardware, it is fundamentally about human usability.
Right.
The human brain is exceptionally poor at memorizing seemingly random strings of numbers, but highly adept at remembering semantic names. DNS bridges that cognitive gap.
DNS is often described as the phone book of the internet, but that feels a bit simplistic given how dynamic it is.
It is a massive, globally distributed, hierarchical database. When you type Amazon.com into your browser, your computer initiates a DNS query. It asks a local DNS resolver, usually provided by your ISP or your corporate IT department, what is the current IP address for this domain?
If it doesn't know.
If the local resolver doesn't know, it traverses the hierarchy. It queries the global root servers, which point it to the top-level domain servers like the .com servers.
Okay.
Those servers point the resolver to Amazon's specific authoritative name servers, which finally provide the exact IP address for the web server.
And this entire global interrogation happens in milliseconds before the web page even begins to load.
It is a triumph of distributed engineering. Furthermore, DNS provides enterprises with absolute agility. If Amazon needs to migrate their web application to a completely new data center with entirely different IP addresses, they simply update their authoritative DNS records.
And the end user has no idea?
None. The next time a customer types Amazon.com, the DNS system seamlessly directs them to the new IP addresses. The customer never even realizes the underlying infrastructure changed.
Without DNS constantly updating and translating those names, the internet would be a completely unusable platform for modern business. You would have to maintain a manual spreadsheet of IP addresses for every SaaS provider, cloud database, and partner portal your company uses.
The internet protocols are incredibly powerful, capable of routing vast sums of data, real-time communications, and secure tunnels. But DNS is the translation layer that actually makes those networks accessible and monetizable by human beings.
Bringing all of these concepts together, we arrive at a deep philosophical split in how network architects view data transmission. The entire chapter really hinges on understanding the dichotomy of connectionless versus connection-oriented communications.
This is the foundational concept that dictates network design, application performance, and troubleshooting methodology.
Let's summarize the core philosophy of OSI Layer 3, the Internet Protocol. As we've established, IP is a strictly connectionless protocol. It treats every single datagram completely independently.
Right.
There is no predetermined path, no established session, and no overarching state maintained between the sender and the receiver.
Building on our earlier metaphor, a connectionless approach is like handing a 1,000-page corporate contract to 1,000 separate bicycle couriers in the middle of a congested city. You give them the destination address in London, and you just release them into the wild.
You don't dictate the route. Courier number 1 might realize the transatlantic fiber is congested and route through a satellite link. Courier number 500 might hit a broken switch in Paris and reroute through Frankfurt.
The sheer brilliance of this connectionless approach is its fluidity. It survives outages, routes around damage organically, and avoids single points of failure. The most direct geographical path is often not the most efficient digital path.
But the chaotic downside is that the couriers arrive at completely different times. Page 500 arrives before page 10, and courier 42 drops his page in the ocean and never arrives at all.
That is the raw, untamed reality of connectionless data transfer. Contrast that with a connection-oriented protocol.
Right. A connection-oriented protocol mandates that a strict, dedicated logical connection must be established between the source and the destination before a single byte of actual data is transmitted. All subsequent messages must use that exact same established connection parameters.
In our analogy, a connection-oriented approach is like chartering an armored truck. You place all 1,000 pages of the contract inside, sequentially ordered. You hire a police escort to lock down a highly specific route through the city, ensuring no other traffic can interfere. The truck drives directly to the destination.
It guarantees flawless, sequential delivery. But the cost is immense. It takes time to negotiate the police escort. It consumes massive overhead to lock down the route. And if a bridge on that specific route collapses, the entire armored truck is trapped. The delivery fails.
Both philosophies have severe trade-offs.
But wait, this is where I have to look at the protocol stack and point out a massive paradox.
What's that?
We established that TCP, the Transport Layer Protocol, is fiercely connection-oriented. It uses a three-way handshake to establish a connection, guarantees delivery, and maintains sequence.
Right.
But TCP hands its data directly down to IP. The Network Layer Protocol, which we just stated, is entirely connectionless. How can a connection-oriented protocol function when it is riding on top of a completely connectionless, chaotic network? Aren't these philosophies fundamentally incompatible?
It appears to be an engineering paradox for sure, but it is actually the ultimate synthesis of the layered OSI model. The genius lies in how the layers abstract reality from one another. You can mix the modes to achieve maximum efficiency.
Walk me through the mechanics of that synthesis using our contract.
The TCP software running on the server in New York is connection-oriented. It communicates with the TCP software on the CEO's laptop in London. They establish a virtual connection. TCP carefully slices the contract into numbered segments and promises to deliver them in order.
But TCP doesn't actually touch the network cables. It has to hand those numbered segments down to Layer 3, the IP protocol.
Exactly. When TCP hands the segments to IP, the IP protocol ignores the virtual connection entirely. It treats those segments as completely independent, connectionless datagrams. IP unleashes them onto the chaotic internet, letting them bounce dynamically through routers, taking different paths, and occasionally getting lost.
So IP utilizes its rugged, connectionless nature to guarantee the data survives the journey, regardless of physical network outages.
And when that messy, out-of-order pile of datagrams finally washes up on the shores of the London network, the receiving IP layer hands them back up to the receiving TCP layer.
And TCP, acting as the QA manager, looks at the sequence numbers, realizes page 42 is missing, requests a retransmission, and finally reassembles the contract in perfect order before presenting it to the CEO.
The paradox is resolved through layering. The strategic takeaway for corporate managers is that this layered architecture provides your enterprise with the absolute best of both worlds.
You get the resilience and the guarantee.
You gain the resilient, autonomous, self-healing routing of a connectionless Layer 3 network combined seamlessly with the guaranteed, error-free assembly of a connection-oriented Layer 4 protocol.
It provides the stability required for enterprise operations, while maintaining the flexibility required to survive the internet. And tying it all back to our opening hook regarding the digital real estate crisis. By mastering these network layers, by deploying CIDR to optimize your allocations, leveraging NAT to protect your internal assets, and proactively transitioning to a dual-stack IPv6 architecture. You ensure your enterprise never suffocates from a lack of connectivity. You maintain absolute strategic control over your global routing, regardless of how massively your infrastructure scales.
You transition from being constrained by legacy network limitations to being the active architect of your own digital expansion.
But building the highway and establishing the traffic rules is only the infrastructure phase. How does the actual software sitting on your employee's screen, the CRM platform, the cloud database, the web portal, how does it interface with this complex transport highway to actually generate business value? In Chapter 6, the session, presentation, and application layers, we are going to ascend to the top of the OSI model to solve the final piece of the puzzle. Managers, you must stay tuned for this chapter. We are going to explore how application layer architectures and ports can either empower your workforce to achieve incredible productivity or introduce catastrophic security vulnerabilities that could compromise your entire corporate data structure.
The lower layers deliver the raw data, but the upper layers dictate what that data actually means to the business. It is where engineering strategy meets the end user.
If you found today's deep dive valuable, remember to like, subscribe, and share. Direct your engineering teams and IT directors to the description below for links to our corporate resources, architectural diagrams, and advanced technical reading. Furthermore, review our channel for other corporate IT playlists and modules designed for continuous professional education. You definitely won't want to miss our other strategic deep dive series, specifically the Digital Forensics series and the Network and Systems Security series.
As your organization scales into the next decade, are your network layers communicating seamlessly, or is a rigid, outdated IPv4 architecture quietly suffocating your future growth?
Align the strategy, optimize the network. Until next time, keep your business connected, your assets visible, and your infrastructure secure.